How does change in pressure affect the equilibrium position of a reversible reaction? Change in pressure is not as straightforward as change in temperature, right? There are certain conditions that must be met for pressure to even have an effect on a system at equilibrium or the equilibrium position of a reversible reaction. One, it must be what? A gaseous system. And two, the number of moles of the gaseous molecules of the reactants and products must not be what? Equal. Number of moles of gaseous reactants and products must not be equal. Now, it is important that you understand these two conditions, because if you don't understand how these two conditions work, then you will always get the analysis of the effect of change in pressure on an equilibrium position of reversible reaction wrong. I can attest to that. So, what is a gaseous system? How do you know that a system is a gaseous system? A gaseous system has at least one gas among the species in the reaction. Either one reactant or one product, or all of them are gases. So examples of gaseous systems are this. We have ammonia reacting with hydrogen to give us, sorry, that's nitrogen, not ammonia, sorry. Reacting with hydrogen to give us what? Ammonia. Hydrogen gas reacting with iodine vapor to give us hydrogen iodide gas. We have sulfur oxide or sulfur dioxide reacting with oxygen. Both of them are gases to give us sulfur 6 oxide or sulfur trioxide molecule. We have calcium carbonate decomposing to give us calcium oxide solid and carbon dioxide gas. Stay with me, we are going somewhere. And then we have iron and steam reacting, iron metal with steam reacting to form triiron tetraoxide, or what we call iron 2 diiron 3 oxide, and hydrogen gas. So you can see all these are gaseous systems. Why? Because they contain at least one gas. Now, let me number this. 1, 2, 3, 4, and 5. Now, from 1 to 5, they all contain what? Gases. Equation 1, all of them are gases, so it's the gaseous system. 2, all of them are gases, gaseous system. 3, all of them are gases. 4, not all of them are gases, but this is a gas, so it makes it what? A gaseous system. It doesn't matter there is no gas on the reactant side, that's irrelevant, but provided there's a gas here on the product side. If this gas was on the reactant side and none on the product side, to have also qualified it as a gaseous system. And now here you have gas on the reactant side and gas on the product side, steam and hydrogen gas. Good. So all of them have fulfilled condition what? 1. Now let's move to the second condition. The number of moles of gaseous reactants and gaseous product must not be what? Equal. So how many gaseous reactants do we have for reaction 1? Change the number of moles here is what? We have 1 plus 3, that's 4. Here we have what? 2, right? So change the number of moles is what? 2 minus 4, which is what? Minus 2, right? Okay. For reaction 2, what's the change in number of moles? How many reactants do we have? Number of moles of reactants? 2. Product? 2. 2 minus 2. That gives us what? 0. So it means they are equal, right? Okay. Reaction 3, change 3 moles of reactants, gaseous reactants, and 2 moles of gaseous product. So you have 2 minus 3. That's what? Minus 1. Now reaction 4. How many moles of gaseous reactants do we have? None. 0. How many moles of gaseous products do we have? 1. So we have 1 here and we have 0 here. So we have 1 minus 0. It gives us what? 1. And now reaction 5. How many gaseous reactants do we have? We have 4. Yes, the total number of moles of reactants is 7. But out of those 7, only 4 are gases, while 3 are what? Solids, right? So coming also to the products, we have 5 moles of products. But out of those 5, only 4 are gases and 1 is what? Solid. So we have 4 moles of gaseous reactants and 4 moles of gaseous products. And that is what? 4 minus 4. It gives us what? 0. So from our second condition, we said number of moles of gaseous reactants and products must not be what? Equal. So which means that if we were to change the pressure of these 5 systems, it is only the equilibrium position of 3 of them that will be what? Affected. Because reaction 2 and reaction 5 do not meet the second condition. The number of moles of their gaseous reactants and products are equal. So change in pressure will not have an effect on the equilibrium positions. So having understood this, let's now look at how increasing the pressure or decreasing the pressure will have an effect on the equilibrium position. Follow me. Before we move on to the next point, look at this. The change in number of moles is negative, here is positive. What does that mean? For the change in number of moles to be negative, it means there's a decrease in what? Volume. And where it is positive, it means there's an increase in volume. And why is that so? This is true because according to Avogadro's what? Law, volume is directly proportional to what? Number of moles. Are we together? So when there is a decrease in number of moles or molecules, there is a decrease in what? Volume. And when there is an increase in number of moles or molecules of a gaseous system, there's also an increase in what? Volume, right? So also remember that according to Boyle's law, that pressure is inversely proportional to what? Volume. So we are going to use these 2 laws in explaining the effect of changes in pressure on the equilibrium position of a reversible what? System. All right, let's roll. So increase in pressure. When you increase the pressure of a gas, what are you doing? You are indirectly decreasing the volume, is it not? Good. So an increase in pressure favors the side with what? With the lower number of gaseous molecules. Right? So now, like I said, it's not as straightforward as temperature. where you can say favors the forward reaction or favors the backward reaction. It depends on which part of the reaction has a lower number of what gaseous molecules, right? And then why is that so? Because increase in pressure does what? Leads to what? A decrease in what? Leads to a decrease in volume, right? Increase in pressure leads to a decrease in what? Volume. And a decrease in volume is directly proportional to a decrease in what? Number of gaseous molecules, right? So that is why an increase in pressure will favor the side with the lower number of what? Molecules. So if we take ammonia for example, let's say ammonia, N2 gas plus 3H2 gas, that's the industrial manufacture of ammonia, giving us what? 2NH3 gas. When you increase the pressure of this system, right? Increase in pressure shifts equilibrium position to the right. Are we together? Favors the forward reaction. And that does what? Increases the yield of ammonia. Because here now a specific reaction, so we can define direction, right? If we use another reaction, let's say the thermal decomposition of calcium carbonate, CaCO3 solid, giving us calcium oxide solid plus CO2 what? Gas. Increasing the pressure of this system will do what? Will move the equilibrium position to the left, right? Because that is the side with a lower number of what? Gaseous molecules. Are we together? So here it will what? Shifts equilibrium position to the left, favors the backward reaction, and does what? Decreases the yield of calcium oxide and CO2, right? So when now comes to decrease in pressure, it will just be the opposite of this. So decrease in pressure, like I said earlier, when you decrease pressure, you are doing what? Increasing the volume according to Boyle's law, right? So a decrease in pressure does what? Leads to an increase in volume, right? Which does what? An increase in volume is directly proportional to an increase in what? Number of what? Molecules, is it not? So this action will favor what? Favors the side with what? With a higher number of gaseous molecules. So if you go back to our ammonia, to our industrial manufacture of ammonia, that's the HEPA process from nitrogen and hydrogen. So you see that decreasing the pressure will do what? Will shift the equilibrium position to where? To the left, because that's the site with the higher number of gaseous what? Molecules. Shifts equilibrium position to the left favors the backward reaction, and then does what? Decreases the yield of ammonia. So, whereas if we decrease the pressure of the system for the thermal decomposition of calcium carbonate, it would be the opposite of all this, right? To shift the equilibrium position to the right, because that's the side with the higher number of what? Gaseous molecules. It will favor the forward reaction and increase the yield of what? Calcium oxide and what? Carbon 4 oxide. So that is that on the effect of change in pressure on the equilibrium position of a reversible reaction. So we move on to concentration.